Hey everyone, let's jump right into this. We are about to explore a hidden reality that's happening all around us, literally right at this very second. In today's explainer, we're unpacking the totally mind-bending, invisible world of subatomic chain reactions. We're going to see exactly how the universe operates at its most fundamental level and how physicists are engineering these massive machines to intentionally ignite some of the absolutely weirdest chain reactions known to science. Now, you might think of your immediate environment as, relatively stable and quiet. But the reality? You're currently standing right in the middle of a torrential, invisible downpour. The sheer density and the constant flux of subatomic particles all around us is just staggering. I mean, did you know you are completely surrounded by invisible subatomic chain reactions every single second of your life? Okay, let's dive into this. We are literally swimming in an invisible particle soup. As we speak, roughly 100 billion neutrinos forged in the sun are passing right through your thumbnail, every single second. You're also being bathed in a constant rain of muons, born from cosmic rays just crashing into Earth's upper atmosphere. And okay, here's one of my absolute favorite facts. Even a humble banana sitting on your kitchen counter right now, it emits positrons. That's the electron's antimatter counterpart. So there's this whole universe of fundamental particles constantly in motion, setting off complex, weird chain reactions that effortlessly evade our normal biological senses. So if our biology can't detect them, how do we actually know they're there? Well, as a particle moves through a material, it essentially drops a trail of subatomic breadcrumbs. These give away its otherwise invisible trajectory. And these breadcrumbs generally come in three distinct forms: light, heat, or electric charge. Basically, every particle detector ever built is engineered to look for one or more of these exact things. They translate those microscopic energy deposits into macroscopic signals that scientists can then record, analyze, and turn into breathtaking maps of matter. Our ability to capture these subatomic hieroglyphs has evolved incredibly over the last century. Back in the 1930s, physicists used cloud chambers. These were filled with alcohol vapor just on the verge of condensing, where passing particles would leave these delicate, wispy contrails, which is famously how we first spotted the positron. Then, fast forward to the 1950s, we got bubble chambers. These often used liquid hydrogen and allowed scientists to capture graceful, iridescent spirals of bubbles trailing right behind the particles. But, to find the really rare particles, we needed to go digital. So in 1968, the multi-wire proportional chamber was invented. It used a fine array of high-voltage wires to record electric charges, capturing millions of particle tracks per second and sending all that data straight to computers, a real game changer. Section 1. Igniting weird chain reactions. See, modern physicists don't just sit around waiting for cosmic rays or bananas to drop breadcrumbs anymore. They engineer massive colliders to force the issue. But when you smash high-charge beams together at ultra-relativistic speeds, we're talking nearly the speed of light here, you encounter a wild phenomenon called beam strolling. This is the intense radiation generated during these incredibly energetic collisions. And it's a massive challenge because it produces this huge flux of secondary high-energy electrons, photons, and positrons. These aren't necessarily the exotic particles you're looking for, right? You're essentially spawning a chaotic cascade, an incredibly weird chain reaction of secondary particles that completely floods the detector with background noise. When we simulate the beam-induced background inside a proposed muon collider, the sheer density of the data hits is wild. When particles like muons decay or collide, their decay products interact with the accelerator lattice, producing massive amounts of secondary particles. It creates a chaotic, literally blinding storm of data that makes finding the actual clean collision event incredibly, incredibly difficult. It's like finding a needle in a haystack if the haystack was actively exploding. So to handle this storm, scientists have to meticulously chart the noise. When mapping out the staggering neutron hit rates across different regions of a detector, you'll find the fluxes are drastically higher in the inner parts of the detector, closer to the beamline, and then they drop off in the outer regions. Physicists absolutely have to understand this background noise perfectly, because if they don't map out these chaotic chain reactions, they'll never, ever be able to filter them out to find those true, ultra-rare signals hiding within. Section 2. Tracing subatomic breadcrumbs. So how do they actually filter out that noise and find the real physics using all this ingenious hardware and software? Let's see how this builds into a cohesive picture using cutting-edge algorithms, specifically things like the Pandora particle flow algorithm. It basically works in three distinct steps. First, it uses combinatorial Kalman filter, or CKF, track reconstruction to find hits in the inner trackers. Second, it selects collimator hits by filtering for specific time windows and energy thresholds. And finally, it feeds both those tracks and the collimator hits into the Pandora PFA algorithm itself to reconstruct the actual particle flow. It essentially takes raw, super messy data points and pieces them together to build a precise 3D image of the chain reaction. But of course, software needs great hardware. To reject all that background noise, detectors rely on two main strategies: extreme spatial precision or extreme timing precision. On one hand, we have technologies like micromegas, which offer high spatial resolution down to 50 micrometers. On the other hand, we have technologies focused on sub-nanosecond timing, like picosec detectors. These can measure down to an astonishing 25 picoseconds. Just think about that. By knowing exactly where a particle was, down to the micrometer, or exactly when it arrived to the trillionth of a second, scientists can separate the real collision signals from the chaotic background noise. Section 3. Designing tomorrow's colliders. Armed with these incredible detection technologies, the scientific community is actively designing the heavy-duty machines of tomorrow. Right now, CERN is evaluating a massive proposed project called the Future Circular Collider, or FCC. This would be a 91-kilometer ring succeeding the Large Hadron Collider. The feasibility report outlines 2 stages for this. Stage 1 is an electron-positron collider serving as a Higgs factory. And get this. This initial stage alone comes with an estimated construction cost of 15 billion Swiss francs. Stage 2 would follow much later, replacing it with a proton-proton collider operating at an unprecedented collision energy of around 100 tera-electron volts. Another incredible concept on the drawing board right now is a 3 TeV muon collider. But remember those weird chain reactions we talked about earlier? Well, because muons are inherently unstable particles, a 1.5 TeV muon beam would result in about 200,000 muon decays per meter. 200,000. Just imagine the intense beam-induced background, the absolutely massive chain reactions of secondary particles that scientists and their algorithms are going to have to conquer just to make this machine a reality. So the crucial point here is perfectly captured by this kind of poetic summary of the particle physics mission. Smash the beam, ignite the spark. We are chasing shadows running through the dark. Whether it's an electron-positron factory or a 100 TeV behemoth, physicists are relentlessly pushing the boundaries. They are purposely igniting the most complex chain reactions in the universe to chase down the remaining secrets of the Standard Model and, to see what lies beyond it. As we stand on the brink of these massive multi-billion-dollar investments, you really have to wonder. We've mapped the breadcrumbs, we've built the algorithms, and we are designing the ultimate colliders. So what hidden reality will the next 100 TeV chain reaction reveal? It's a fascinating question for sure, and one that promises to completely rewrite our understanding of the universe. Thank you so much for joining me on this explainer, and keep questioning the invisible world around you.